Shalom to everyone. It's very good to see all of you. If you want to turn on your cameras, it's nice because then I can see with whom I'm talking to, but it's up to you. Today, I'd like to tell you about a paper that was just posted to the archive called Natural Dynamic Reduction of the Three-Body Problem. Last year, I told you about progress towards a statistical solution of the problem. This one is also progress, but not towards the solution, but towards an improved formulation of the problem, okay, an improved formulation. The paper appeared today after a delay of 1 day due to the archive. They're not as quick as they used to be, but fortunately it is up there, and you can have here the archive number. And just to tell you already in the beginning what the paper is about, I will read the abstract for you, okay? And please feel free to ask any questions as we go along. So the three-body problem is a fundamental long-standing open problem with applications in all branches of physics, including astrophysics, nuclear physics, and particle physics. Because you can have three bodies, which could be stars, nuclei, particles inside the proton. In general, conserved quantities allow to reduce the formulation of a mechanical problem to fewer degrees of freedom, a process known as dynamical reduction. However, extant reductions are either non-general or hide the problem symmetry or include unexplained definitions. This paper presents a dynamical reduction that avoids these issues and hence is general and natural. Any three-body configuration defines a triangle. The three bodies define a triangle and its orientation in space. Accordingly, we decompose the dynamical variables into the geometry, and the geometry is a funny name for the shape of the triangle and the size of the triangle. Okay, if anybody can think of a better name, I'll be happy to hear. So triangle geometry, I mean shape of the triangle and its size. So on the one hand, we have the geometry, and on the other hand, we have the orientation of the triangle. So we decompose it to orientation and geometry. The geometry variables are shown to describe the motion of an abstract point in a curved three-dimensional space subject to a potential derived force. So we have a potential and a magnetic-like force with a monopole charge. The orientation variables are shown to obey dynamics analogous to Euler's equation for a rotating rigid body, only here the moments of inertia depend on the geometry variables rather than being constant. So we'll explain all of that in a while. The reduction rests on a novel symmetric solution to the center of mass constraint inspired by Lagrange's solution to the QB. So that we'll explain that. And the formulation of the orientation variables is novel and rests on a little known generalization of the Euler-Lagrange equations to non-coordinate velocities. Applications to special exact solutions and to statistical solution are described. Okay, so this is the abstract. And accordingly, the outline of the talk is going to be okay, so we have here the title, we have my name, I think everybody here knows me, and we have the date and the archive number, and here is the outline. So we'll explain the problem. It takes 1 minute to define it, but then we'll discuss it a bit. And then we'll discuss these two key points, the coordinates for a center of mass frame and the orientation geometry decomposition. The first one will introduce a variable W, and the second one will use the angular momentum J. And then we will discuss applications and perspective. So let's start. So the three-body problem we have three bodies, which we consider to be point-like, with masses m1, m2, m3. They have three positions, three velocities, shown here as black arrows, velocities. And they have some forces, three forces between any two pair of them. These forces could be Newton's gravitational forces, or could be any other forces. It will not be important for this paper. What will be important for this paper would be mostly the kinetic energy, and only that the potentials depend on the distances. So for instance, it could be, the force law could be Newton's, and the Lagrangian would look like this, just a standard kinetic term and the potential between any two objects. So far, it should be very easy, but if there's any question, please ask me. Oh, and what's the initial value problem, of course? We have initial positions and velocities, and we want to predict the future, or in this paper, we at least want to formulate the equations of motion, but in some simpler variables, not in the variables RA and RA dot, the positions and the velocities, but in some improved variables. So a bit of background. Before we do three-body, we have to discuss two-body, because two-body was one of the great successes of science of all times, when Newton was able to explain planetary motion using his universal law of gravitation. And that was a great success. And in fact, it was possible to fully solve the two-body problem. With two bodies, wherever they start and with whatever velocities, you have an exact mathematical solution for all time. And the solution, as we know in the reduced space, is a conical section, an ellipse for the bounded case. But every success gives us ideas. And then Newton got the idea, what about the three-body problem? So that leads us naturally to the three-body case. He was interested in it for a very concrete reason, to understand the motion of the moon, where to zeroth approximation, it just encircles the Earth, but there are corrections to that, which were known already to the ancients, and they are caused by the sun. So it's a three-body problem. You need to understand it. Okay, so here I will not go through all of history. I will just mention some highlights to give us a flavor of the long and deep history of this subject. So first, it was applied to the moon, and perturbation theory had to be developed for that. Then there were exact solutions, so-called central configurations found by Euler and Lagrange. Oops. Oh, yeah. Sorry. Yeah. Okay. Then the Poisson bracket and the secular approximation were invented in the context of planetary motion, which means a sun and two or more planets. Chaos was discovered when Poincaré studied the three-body problem. So that's extreme sensitivity to initial conditions, which makes an exact solution to all times impossible, we believe. Poincaré also invented modern topology, and he was influenced by the three-body problem when he did so. So that's homology and homotopy. And when computer simulations became available, that again revolutionized the field, allowed to simulate solutions, and brought about a statistical theory of the motion of the three-body system. So these are some of the subjects, and here are some of the researchers, authors on the subject. So Newton, D'Alembert, Clairaut were involved with the moon, and then the moon was settled. And then Euler and Lagrange went to the general three-body problem with any masses. Laplace was also involved. Gauss and Jacobi were interested in various aspects, Hill, Poincaré. And in the 20th century, it was put aside a little bit because there were other interesting things and it was thought to be unsolvable, but still, Levi-Civita worked on it, Lemaitre, And in the context of the helium atom, Hilleras and Fock, I'm be missing one L in Hilleras names. And computer simulations, Agekian and Anosova, Valtonen, Monahan with the statistical theory, Heggie, Hatt, and Macmillan, computer simulations. So that's more recently. And there's also a vivid mathematical community. I mentioned Smale, who defined central configurations to be one of the challenges for the 21st century. So he defined it in the year 2000. That's related to the three-body and more generally n-body problem. There were exact solutions, periodic solutions, which are numerical or, well, not numerical, but not in closed form, by Chris Moore, Shensineer, Montgomery, and Meckel. We'll discuss their contribution also later. And finally, with the Kozai-Lidov oscillations for the hierarchical system, we have two persons who were educated in part of their career in the Hebrew University, Smadar Naos, today from UCLA, and Chagai Peretz, I'm not sure if he's with us or not, from the Technion. And finally, our Nick Stone made the contribution to the statistical theory, which I will mention in more detail later. Okay, so this was very brief, just to give us some flavor. So back to our objective. We would like to find a dynamical reduction. That means to choose variables or simplify the dynamics through choice of variables. The conserved quantities enable such a simplification because it tells us that motion is limited to some submanifold of phase space. So we can, if our phase space variables are compatible with the conserved quantities, then we should be able to use fewer coordinates in phase space once we know the initial conditions and the conserved charges. So some examples of dynamical reduction, although different than what we'll see today, small oscillations with more than 1 degree of freedom. We know we can always decouple it to a decoupled sum of one-dimensional oscillators through normal modes. So that's complete decoupling. That's not what we'll have here. Another example is the reduction of the central force, where we can reduce it to an effective radial problem once we add an effective potential. Our case will also be different. We won't be able to reduce, but we'll be able to, well, partly reduce and partly decompose into two systems. We'll see that. But this is just to give you an idea of what I mean by a dynamical reduction. How did I get here? Okay, so a year and a half ago or something of the sort, Stone and Lee published a very interesting approximate statistical solution in closed form. And that was very exciting, and I got drawn into that. And I developed a flux-based theory. And within this flux-based theory, I was interested in computing the regularized phase space volume. So you have all of phase space, and you have given the conserved quantities, you want to know the phase space volume. So that's just integral over all phase space variables with delta functions, which I write here schematically for all the conserved quantities. And when you compute these integrals, you can perform some of the integrations analytically. And the remaining few have to be done numerically. And that gave me the idea that maybe this miracle has a reason. Maybe the analytic integration is possible due to some dynamical reason, not only in this integral for the phase space volume, but more fundamentally for the whole formulation, the whole dynamical problem, if you like, the whole Lagrangian. So that was the hint. And we've been developing it also, this regularized phase space volume, and it should appear shortly with the collaborators Dan Dekar, Mazumdar, and Lederer. Some of them might be here. Yes, I see that Yogesh at least is here. Great. And Ginat and Peretz, Ginat is here from the Technion. They made an important improvement over the Stone and Lee paper. So this still belongs to the statistical solution. I don't want to discuss the statistical solution today, only the formulation, but I just mentioned that that was the reason that brought me to this research. Great. So now I'd like to start really with the first physical topic, which is how do you choose coordinates for the center of mass frame? Sounds like a very simple question, but we'll see that an interesting and novel answer to that allows us a new point of view and allows us to make progress for the whole problem. We'll see. So the usual coordinates are the 3 position vectors. So we have 3 vectors or 9 degrees of freedom. But because of conservation of linear momentum, of course, we work in the center of mass frame. So we want these 3 vectors to be constrained by the center of mass constraint, I call it. So it's 1 vector constraint equation. So the true number of degrees of freedom is the difference, 2 vectors or 6 degrees of freedom. Let's recall what was done in the 2-body case. There was no issue. We went to the relative position, R equals R1 minus R2. And that's a great choice. It's independent of translation, so it decouples from the center of mass. If you look at the kinetic energy, to decouple from the center of mass coordinate, you need the other coordinates to be translationally invariant, so to be only separations. So there's only 1 separation for a 2-body. And there's just small ambiguity relating to the sign of this, whether I take R1 minus R2 or R2 minus R1, but it's a small difference. And if I square it, it disappears. So that's the standard thing for the 2-body. What are we going to do for the 3-body? For the 3-body, we can use the relative positions, RA, B equals RA minus RB. So there are 3 of them only this time. And we wanted to have only 2 vectors to describe the coordinates. So we have too many. And indeed, they're not independent. They satisfy, by definition, this constraint. So we have to make some choice. We can't just take these 3. Okay? So either you work with these 3 and with constraint, or you make some choice. Let me show you 2 popular but non-symmetric choices. So they break the permutation symmetry of the problem. The first one is the planetary coordinates. When one of the masses, say star, is much larger than 2 others, say planets, as you see in this figure, then we can take the 2 vectors to be the vectors from the star to the planets. Okay, so it makes sense. But that assumes some hierarchy of masses. Another possibility is to assume a hierarchy of distances or a lunar situation. So this one would be the sun, and here we would have the moon and the earth. And then it's natural to take the separation of the binary, call it R12, and the separation between the sun, or the 3rd one, and the center of mass of the binary, that would be the 2nd coordinate. Okay, so these are popular choices, but I think it's evident that they break the permutation symmetry, and so they're not appropriate for the non-hierarchical case. So what is appropriate for the non-hierarchical case? I'll just show you my suggestion. So it is inspired by Lagrange's solution to the cubic. The solution from the cube for the cubic was known, I think, since the 15th century in Italy. By cubic, I just mean the 3rd degree polynomial. But Lagrange developed a new method with new insight how to solve it. And So Lagrange appears here again. And following his variables, I define the vector W to be a complex vector. R1, R2, and R3 were real vectors, but W is a complex vector defined as so a linear combination of R1, R2, and R3, where eta is a cubic root of unity, and I denote here the complex unit by J, not by I. I'm not doing it because I'm an electrical engineer. I'm doing it because later I will use I for a different purpose. We will have here two imaginary units, okay? So this one is denoted by J, its square is -1. So you can see it's a bit like the two-body problem where we defined it to be R1 minus R2 in the sense that if I make a translation, I add a constant vector to all vectors because 1 plus eta bar equals to 0, then if I add a constant and to all the R's and perform a translation, W will stay the same. But the more important property of W is that it transforms nicely under permutations. That's not difficult to see. If I change the labels 1 to 2, 2 to 3, 3 to 1 in a cyclic manner, then it's like multiplying W by a phase, a third of a revolution, or eta bar. On the contrary, if I don't do a cycle, but I do an exchange, say 2 and 3, then W just goes to W bar, because if I change 2 and 3, then I exchange eta and eta bar. So this is just J conjugation. And any general permutation can be generated from these two. So it will be a combination of conjugation and multiplication by a phase. So that's quite symmetric. It's not absolutely symmetric, the same way that in the two-body problem, there was a sign ambiguity. Here there is this phase and conjugation ambiguity, but in some sense, I think it's a very nice transformation properties. So this is going to be the definition of the coordinates that we use. Because it is a complex vector, it has indeed 6 degrees of freedom. Okay? So we'll have 3 degrees of freedom for the center of mass, and then 6 degrees of freedom for W. And now we should continue the reduction with W. So this is a central result of this paper, the novel definition of this W. It's true it's a definition, but I consider definitions also to be important results. Any questions about the definition of W before I proceed to the remainder of the reductions and reduction steps and the final formulation? In fact, I will skip rather directly to the final formulation from now.
I have a question. Do you know perhaps to give any, say, physical meaning to multiplying W by a phase? Say, how does it look in, say, phase space, or is it simply a sort of mathematical property, which is nice?
Yes, it's quite abstract. You take a real vector and you multiply it by a phase, and now it becomes a complex vector. So we kind of added more dimensions. We added new dimensions to the problem that we didn't know were there. We were thinking only in terms of real vectors, but now we're going to complex vectors. Thank you, Jonathan, for the question. And in the same way that we do so in algebra. In algebra also, we can have a real cubic. There is nothing complex, but still, in order to find the solutions, we find ourselves drawn or led to consider complex numbers. Something similar happens here. So what are going to be the following steps? They're all detailed in the paper. Here I will just mention them very briefly and skip directly to the final answer to give you the whole physical picture. So first step is to reduce over translation. We've already done it, and that introduces the complex vector W, three-dimensional vector. Then we're going to reduce over rotations, and there's associated a conservation of angular momentum, and that will take the three-vector W, and since every configuration is planar, we can consider W to be two-dimensional. I will draw that as W without a vector. But then we also have to take care of rotations through the omega vector, angular velocities. The third step will be to take care of rotations within the plane. For a reason that I'm not explaining now, this will be equivalent to looking at the quotient space of the two-dimensional complex plane divided by the action of multiplication by a phase, a U1 which multiplies by a phase. So that will take us from W, which was a 2D complex vector, or 4 degrees of freedom, real degrees of freedom, to something that we call the vector G, or geometry space. I will explain that a bit later. And finally, the fourth and final step would be to transform from velocities to momenta. So it's a Legendre transform. So we'll use angular momenta rather than angular velocity. So I have to go through all of these steps. In the appendices, I discuss some cute relations with other problems. So we'll have to discuss non-coordinate velocities and a generalization of the Euler-Lagrange equations. And that would allow us to formulate the usual rigid body, but in a Hamiltonian or Lagrangian equations. This is something that we usually don't do. We usually do it only in Euler angles, but we'll be able to do it in terms of omega and j, and we'll get Euler's equations of motion from this Lagrangian or Hamiltonian, again, in terms of omegas alone, not in terms of Euler angles, which hide the symmetry a bit. Then we'll also discuss, another appendix discusses bicomplex numbers. These are numbers which use two imaginary units, I and j. It will be related to the w's over here. So the w's were complex vectors in 2D, but then if I complexify the plane, then I just get 4 real numbers encoded by a bicomplex number. And that has a very nice application to the isotropic oscillator, another simple system that we all study in analytical mechanics. So I will not discuss it further probably today, but you can find information about it in the appendices. Okay, so here is the final picture. I have here a figure that shows us everything. After that, we'll have a lot of formulas, but here I want to show you the basic idea all in one figure. I call it the orientation geometry decomposition. So here are the 3 masses. At any moment, they define a plane and they define a triangle, right? Since they define a plane, we have here an object which is rotating. This triangle is rotating. So we can think of this object as a rotation motion. It's not a rotation of a rigid body because the triangle shape can change in size, but it's a rotating object. So it will be described by a system which is very similar to the rigid body rotator, rigid body rotation motion, only allowing the moments of inertia, Ij, to change. In particular, our variables here are going to be the angular momenta in the body frame, in the moving frame. Okay, so this is going to be one component. It's a decomposition, so we'll have 2 components. One component is a rotating body in terms of J, angular momentum in the rotating frame. The other side is the geometry space. Geometry space, that's the space of all triangles. So we all know that in order to specify a triangle, we need to specify 2 angles. The third one, we get it from summing to pi or 180 degrees. So we need 2 angles to specify a triangle and a size. Altogether, it's a 3-dimensional space. Okay? So this is this 3-dimensional space where each point gives us the geometry of the triangle. So I call it geometry space. Again, it's just a size plus shape. So I didn't find a better name. So it's triangle geometry space. And it's a three-dimensional space, so I can use a vector G to denote a point in it, or I can use spherical coordinates, this is G, or spherical coordinates R, theta, and phi, standard spherical coordinates. Within this space, we have two forces acting on the imaginary point which represents the system. One force attracts it to this axis. So this represents the Newtonian potential. So there is an attractive force pulling it to these three axes. In addition, there is a magnetic-like force where we see here these blue arrows. These are magnetic field going outside in all directions, not uniformly, but in all directions. And this is a magnetic field. It originates from Coriolis force because we get this triangle by dividing by rotations within the plane. So there is some rotation within the plane which creates a Coriolis force, and in this geometry space, the Coriolis force manifests itself as a magnetic-like force, which gives us forces proportional to velocities, not only forces which depend on positions, but also on velocities. You may wonder whether by performing this reduction or decomposition, we can make the problem integrable or non-chaotic. The answer is, of course, not. The problem is, in general, non-integrable and chaotic. So now we can ask, where does the non-chaos feature come in? The rigid body is known to be integrable. So I would call this component the core chaotic component. It's a point moving in 3 dimensions, so it's a system with 3 degrees of freedom. By the way, it can be understood as a planar 3-body problem. A problem where all the points, all the masses move only in the plane, and then the rotation motion simplifies. Okay, so this guy is the chaotic core of the 3-body problem. Finally, I need to explain this golden object, which looks like a joint of 3 pipes. This is simply a constant energy surface. So if we know the energy of the point, then we know that it always has to move within this joint. Okay, just usual rule in mechanics. So this is called sometimes Hill's region. So we can tell that the particle can never get out of this golden surface. So motion here inside represents the chaotic motion, but then it can run out. Running out in this direction would mean that particle 2 is ejected, but then it will fall back. Then it will move here some more. Then it may go out here. That means that particle 1 is ejected, but then falls in. Finally, it may be thrown out in some direction, meaning that the system has disintegrated and there's an escape. We call it an escape. Okay, so in this way, geometry space allows us to visualize the system, which had originally too many degrees of freedom. It had 6 degrees of freedom, but the core motion can be projected to this 3-dimensional geometry space, which has only 3 degrees of freedom. And that allows us to visualize, to use intuitions about energy surfaces, and so on. So next, I'm going to show you the Lagrangian, or something similar to a Lagrangian, which defines all of this in terms of formula. But this is the basic picture. So if you want to wait until I show the Lagrangian, that's great. If you want to ask questions now, that's also great.
Can I ask a question, please?
Please, Barry.
Yeah, so, oh, sorry, you can't see me. I don't know, it's not, the camera is not working, sorry. So you mentioned, maybe I misheard you. So it's 2 questions really. First of all, so you said that the rigid body is integrable.
Yes. Mm-hmm.
But then you said that the moments of inertia change also, right?
Yes.
So
there is a tension between the two statements.
Yeah, I think because I as far
yes,
as I
you are
remember,
right. Let me answer. You are right. Let me answer.
Okay.
The rigid body is integrable. I think on that everybody agrees. In this system,
sorry. I think there are only three specific rigid bodies that are integrable, and the general rigid body is not. With general moments of inertia, I mean general, completely.
No, I
At
would
least
say,
that's what it says on Wikipedia.
well, the motion of a rigid body, of a rigid body, maybe it's a matter of definitions. I would call it integrable because it moves in a circle in J space. It closes on itself exactly. And you have the conserved quantities, the energy and J squared. And then you have to, once you solve it for J, once you solve the Euler equations, which I think you can do in general, even for the asymmetric talk, in terms of elliptic functions, then you have to integrate the Euler equations. But it's not important for me for now. I would just say that the geometry space in itself, which describes the planar three-body problem, is in itself already chaotic and non-integrable. And in that sense, I would like to think of it as the chaotic core. If you like a different interpretation, you can take the different interpretation. But thank you for this comment. Maybe it requires some discussion.
Okay, may I ask the second question? It's a short question.
Yes, please.
So can you comment, please, about how this geometry space is related to the shape sphere of the three-body problem, in the sense that the shapes, I mean, this construction that maps the triangles into a two-dimensional sphere?
Yes, very good. Let's see. My next page could explain this a bit. No, it's not here. Oh, it's in the next page.
I'm willing to wait until you get there.
Well, I can give you the basic idea. Let me give you the basic idea. So I think it's a good question, and I'd like to give you the basic idea. So once we discuss the planar motion, then W W is equal to R1 plus eta R2 plus eta bar R3. It's now a 2D complex vector, right? But we want to discuss it up to rotations, because in the plane, you can rotate any triangle and it has still the same geometry. So we want to consider rotations in the plane. We want to define them to be equivalent, these phase rotations, where I is a phase in the plane. So I now think of R1 as being X1 plus I Y1. So I promised you that I will have a different purpose. Okay, so R1, instead of being a two-dimensional vector, is now a complex number with I. And together with the J's over here, I make W, which has the general form A plus BI plus CJ plus DIJ. So it has 4 real components. Previously, we thought about it as a 2D complex vector. Or instead of a 2D complex vector, which has 4 real components, I can think of it as this bicomplex number. and consider it up to rotations. Did it give you some insight? Not full, but at least some.
Yeah, thank you. Yes.
Great. So let me proceed. That's important. Okay, so here is the formulation, and in a moment I will show you another picture of the geometry space, which will add some more insight. So here is the Lagrangian. Well, it's not going to be a Lagrangian. It's going to be L sub j. It's going to be something intermediate between a Lagrangian and a Ruthian. It's going to be a Legendre transform of the Lagrangian just with respect to j. I can also do a Legendre transform with respect to the geometry variables, but I don't need to. Sometimes a partial Legendre transform is called the Ruthian. I'm going to call it a motion potential, because any of these, Lagrangian, Hamiltonian, Ruthian, by taking derivatives, we get the equations of motion. So instead of having a different name for each one of them, just like in thermodynamics, we can call energy, enthalpy, free energy, whatever, we can call all of them thermodynamic potentials. Here I would call it a motion potential, okay? So this is going to be the main object for the formulation, this motion potential, and it's going to be divided into three objects according to the powers of J in it, L0 plus L1 plus L2. L0 has no J, L1 is order J, and L2 is order J squared, okay? And it's going to depend on 6 variables or 2 vectors. One is the angular momentum vector of the rotation degrees of freedom, and the other is the 3-dimensional geometry vector or point in geometry space. It can also depend on G dot. Okay, so this is the Lagrangian, and now I need to tell you what are L0, L1, and L2. L0 is this expression. So it's an expression in terms of it's in radial coordinates, r, theta, phi. We see here the radial, the thing that we expect for a round motion on a round sphere, but then there is some function which depends on r, which depends, on location. So this is called the conformal factor. We have here r, and we have I, which depends on r, theta, and phi. So I depends on geometry space. I is nothing but the moment of inertia of the triangle, which I will define in a moment. Okay. So here we have I dot squared. Here we have this motion on the sphere. And finally, we have the potential, for instance, the Newtonian potential, but as I said, it could be anything else. So what is the definition of I? As usual, the moment of inertia, it's ma/ra squared. And in the center of mass frame, you can also write it in terms of the separations. It's a one-line proof, but we want to go fast, so I'll skip it. R23 squared can be described in terms of the spherical coordinates r, theta, phi by this formula, and similarly, the other distances. This can be shown in geometry space as follows. So this is a great picture. If you know some optics and you know the Poincaré sphere, it would help you, but you don't need to know that. So this is the 3-dimensional space, the geometry space, and I take some sphere in it. It is called the shape sphere. And you see here several special points on the shape sphere. You see the equator. The equator are all the collinear triangles. So these are degenerate triangles, okay? In fact, the z-coordinate is proportional to the area of the triangle. So the equator has z equals to 0, so it's collinear. The top point is the equilateral right-handed triangle, and the bottommost point is the left-handed triangle. So we keep here the labeling on the vertices. So there's a difference between 1, 2, 3 and 1, 3, 2, okay, if you can imagine. So one of them we call the right-handed and the other the left-handed triangle. And there are also 3 special points on the equator when 2 of the points coincide. If point 2 and 3 coincide, we call it C1. And similarly for the other points. Now I will show you how you can see the edge lengths the distances between the particles from the location of the point on the shape sphere. Suppose the point here is somewhere here on the shape sphere. Then what you need to do is to take the distance from it to the different collision points. Say the distance from here to here, the distance squared is nothing but R23 squared. And similarly, the distance to the other 2 points. So it's given algebraically by this formula. But if you think about it for a moment, you'll see that this formula is nothing but the distance on this geometry space. So a point in the geometry space, it's very easy to read from the location of the point, the 3 sizes, the 3 side lengths of the triangle. As we know, the point determines the triangle, and in particular, it determines the side lengths. I've also used here these notations, symmetric polynomials in the masses. So M is the total mass, M2 is this symmetric combination of masses, which has dimensions of mass squared, and M3 is the product of all the masses. So you've seen M here, that was the total mass, and here you've seen M3 and M. So I've now defined all the quantities in the sector of the motion, which is decoupled from J, decoupled from rotation, if you like, for zero angular momentum, or it's also very useful for planar motion. Now let's look at parts which do depend on J. So the part which depends to J at the first order looks like J3 divided by the moment of inertia, which depends on geometry space, as we've seen, times this expression in velocities. So it's linear in velocities, and it looks like a vector potential that was noticed already by Lemaitre in 52, that there is a vector potential appearing here. And actually, it's interesting to compute the associated magnetic-like 2 form. I haven't seen this computation. It's not difficult, but the result is very nice. This is the magnetic-like 2 form. We see here the area form on the sphere. It's only in the sphere, in the angular direction. It's not in the radial direction. If we want the standard magnetic vector, then we need to do a Poincaré dual of it. But this is in the so-called 2 form. And when you look at it, you see also that it has a monopole charge, which sits only at the origin of geometry space. So that's why we had these blue arrows coming out of the picture here. Okay, so that's described by the term B1, all these blue arrows which come out in all directions out of the monopole which sits here in the center. But it's not just a field due to a monopole, but how shall I say? Well, it's a field which doesn't satisfy any Maxwell equations, but if you compute its divergence, then the only place where it has a source is at the origin. Yeah, I think so. Okay, so now we explained L0, we explained L1, the magnetic field, now L2. L2 has a form which is rather familiar for rotators. It couples the J's, J squared, divided by I. And here J's alpha J beta, where alpha and beta run over 1 and 2, times I bar alpha beta, where I bar is associated with the inverse of the I matrix, the inverse of the moment of inertia matrix. So let me define the quantities that we see here. We defined already I. We know what J3 is. J is the angular momentum vector in the rotating frame. Delta squared is defined by this expression. It's nothing but twice the area of the triangle. That's delta. Mass, we define total mass and product of masses. And finally, this I bar is given by these expressions, which are a bit similar to the expression for the moment of inertia, but different. That's because it's easy to invert a 2 by 2 matrix. the moments of inertia have one principal axis in the z direction, perpendicular to the plane, and then within the plane, it's a 2 by 2 matrix, which is easy to invert, so we can have an explicit expression for it, where rhos are the position vectors or position separation vectors in the plane, these bicomplex numbers, and they can be, these complex numbers, and they can be given explicitly like so in terms of the spherical variables in geometry space. Another important property is that the angular momenta satisfy this Poisson algebra with a very famous and important minus sign here. So angular momenta in the inertial frame of reference have a plus here, but in the rotating frame, there is an important minus that we must include. And to know how to obtain this, that's very interesting, and that requires this Poincaré generalization of the Euler-Lagrange equations. But you can do it completely classically. Okay, so now that we have the motion potential Lj, we can get the equations of motion. For the geometry space equations, we have the usual Euler-Lagrange equations. And for the rotation motion, we have a Hamiltonian-like equations of motion. There's a minus sign here because Lj is like minus a Hamiltonian. That's the reason there's the minus sign there. And after we solve for the j's, we should also integrate for some orientation angles, such as the Euler angles. But we can solve for the whole motion first using only this system of equations, where Qs can be thought of to be these spherical coordinates in geometry space. So that's it. That's the formulation. Because we've had already some questions, I think it's better if I just go ahead and finish the few more slides that I have, and then I'll be happy to answer any questions if it's okay with you. So we discussed this decomposition into two subsystems, but this time coupled subsystems. How are they coupled? Maybe I should stress. Here we have both J and geometry space. Both J and geometry space. So for J variables, this looks like the Euler equations. But for the geometry variables, this looks like a centrifugal potential. Similarly, for L1, for J variables, it looks like a precession equation of motion. While for the geometry variables, it looks like a magnetic-like force. Okay, so a single term in the Hamiltonian, as usual, gives us both. It gives us several equations of motion for both sides. So we have this new formulation. It's always good to have a new formulation, but we would like to see something concrete, what can be used it for. And we have a few applications and a few are envisioned. Let me just describe a couple. So we can discuss either to the statistical solution or to the few exact special solutions, special exact solution. So one is to this computation of the regularized phase-space volume that I've already mentioned. I mentioned this when I mentioned the motivation for this work, but now it can also be turned around and thought to be an application. In the statistical theory, the decay rate is inversely proportional to the phase-space volume. It's like a particle escaping a box. The bigger the box, the bigger the box, the lower the decay rate. So we want to know the size of phase space, where phase space is roughly this golden pipe joint. Only at each point, we also have to take into account the momenta. The momenta are not drawn here and not the J variables, but let's think about it simply as so. Clearly, the phase space volume is infinite. However, when you see it, you also get a very good, easy idea of how a meaningful finite number can be extracted. We call it to regularize the volume. What you can do is you can subtract the flat triangles, or more appropriately, the integral over some integrand within. Okay, it's V. I see that you're leaving. Thank you very much for joining us. I appreciate it. So, yeah, so I'm back to this regularization. So we have to take out, we could subtract the quantity which relates to the flat pipes. Since far away this pipe joint becomes flat, then if we subtract the flat pipes from the original quantity, as we see here, we define the regularized sigma to be sigma bare related with an integral inside the golden pipe, minus sigma reference, which is the sum of the three blue pipes, and the difference is going to be finite. And this will be described in full detail in a paper to appear soon with Yogesh Dandekar, as a postdoc here, Shubhajit Mazumdar, who used to be a postdoc here until a year ago, and Lior Lederer, who is an undergraduate student here. Another application could be to a novel derivation of Lagrange's equilateral solution and the determination of its stability. And the reason is that equilibria in this geometry space are the same as rigid rotation, because we're in a rotating frame. So in geometry space, a point that sits here describes an equilateral triangle in uniform rotation, which is nothing but Lagrange's equilateral solution. We didn't review it, but there is such a solution. Similarly for the left-handed one. So we can now easily derive it by looking at the effective potential and looking for minima of the effective potential. This gives us this rather mysterious solutions due to Lagrange, which apply not only for equal masses, but whatever the masses are, an equilateral solution can be made to be an equilateral configuration can be made into a solution. And we can get insight from this geometry space. In fact, here we specialize to the Newtonian gravity problem, and here it's very important the equality of inertial mass and gravitational mass. This usual equality of inertial mass and gravitational mass is key for the existence of these special solutions, the Lagrange equilateral solutions. So this is one application to get known results from a new and different perspective. And we can also show in this way by an usual stability analysis for static solutions, we can I'll say it again. If we want to study the stability of these rotating equilaterals, instead of performing a dynamical stability analysis, in this space, it's enough to perform a static stability analysis around an equilibrium point. So conceptually, it's a bit easier, and one gets known results, and we'll try to push it also maybe to get additional results. So these are some applications we saw for the statistical solution, and we saw for exact solutions. Some perspective. So far I showed you the formulation, but many ingredients were already known, while some are novel. So I'll try to tell you briefly now. I don't think it's very important for first hearing, but I'll try to tell you briefly what was already known. Newton formulated the problem, of course, first using Newton's laws of motion, R1, and I should cancel this M1 here, right? And that's the Newtonian formulation. Then Lagrange had a very interesting formulation, which is very close to what we did today. He used as fundamental variables the shape of the triangle, or more specifically, the side lengths squared. But so he was able to write an equation for that, but that wasn't enough, and he needed more equations. But that's a very interesting formulation that Lagrange did in 1772. It was in answering to a prize by the French Academy of Sciences, and a side product of this research was the discovery of the Lagrange solutions. So he used here novel variables. Jacobi was able to eliminate one more variable that's called the elimination of the nodes. After Poincaré, in the 20th century, Levi-Civita formulated the problem, decomposed the rotation out of it, used the omega, and was the first to use a motion potential. So Hamilton invented it already in the first half of the 19th century, but apparently it wasn't used for this problem, or maybe it was, but that's the first one that I know. Then in the 30s, mathematicians, Murnaghan and Van Kampen and Wintner from Johns Hopkins in Baltimore found used side length squared, the symmetric variables, to describe first the planar problem, then the full three-dimensional problem. This one requires 3 degrees of freedom, like our geometry space. This one requires 4 degrees of freedom. It's like geometry space and one extra angle instead of our rotating body. Lemaitre in 52 already defined the same symmetric coordinates that we did in geometry space, but he didn't have this definition of W, and therefore his definition was somewhat mysterious, and he arrived to it in a rather roundabout and miraculous way. And the definition of W gives us a straightforward way to reach the same coordinates that Lemaitre found in 52. Finally, I will mention Meckel and Montgomery that more recently defined the term shape sphere and modernized the mathematical discussion and described all the reductions here, but they did everything in the planar context. I will also mention that surprisingly, quantum theory helped here, because if you're interested in the spectrum of the helium atom, you're actually interested in a special case of the three-body problem, a special case where two bodies have the same mass, the electron mass, and the nucleus at first can be taken to have infinite mass. Later, you can also include back reaction for that. And that was dealt in the early days of quantum mechanics by Regularized. He found a formulation with 3 degrees of freedom, the separations, but that held only for 0 angular momentum, the so-called S wave for the helium atom. Then there were some other ones, but I think it would be enough for now if I just flash it. It would be too much for now, but there were some other interesting formulations which has interesting touching points with what we discussed today. So the geometry space vector was something similar, was found by Grunwald and later done in full by Murnaghan and by, well, not by Murnaghan, but by Lemaitre. And Fock did a bit after Lemaitre, introduced, however, this 4 variables, which once divided by the angle give us the 3 variables. Okay, so I'll just repeat that our novelties is the definition of W and the formulation in J. Maybe there are a few other novelties, but these are the main novelties and putting the whole picture together. Okay, so let us recap We're just a few more minutes after 4, so I think we're fine. So we described a novel formulation of the three-body problem, where we divided the degrees of freedom, not to the degrees of freedom of one of the objects and then, but rather in a symmetric way, which does not, has no prejudice against any one of the bodies. They're all equal, it's all symmetric. We have a rotating part, and we have a geometry part, where each point describes the geometry of the triangle, namely the size and shape. And we gave explicit expressions for the motion potential, which describes the motion in this way. And in order to reach it, we use this definition of W with the cubic roots of unity, the complex vector W with the cubic roots of unity. So we have here two main results, two novel main results. One is the definition of W, and the other is the result for the formulation of LJ. So with this, I thank you very much for your attention, and please, if there are any questions, I'm happy to answer, of course.
Barak, hi, it's Hagai.
Shalom, Hagai.
So I was wondering whether you can make use of this really nice way of looking on all these problems. What would happen when you have one of the particles is a test mass? So we have a conservation for the two other bodies. How would that look like in this type of view?
Okay, so you're asking about the hierarchical case, which is against the rationale of this formulation. This formulation is constructed for the non-hierarchical case, where all the masses and distances are comparable. But let's, for the sake of the question, see what happens in the test mass case, where one mass is much lighter, and then the two other masses are moving in a two-body motion. And the third guy is moving in their background. That's known as the restricted problem. And then in this case, we have only 3 degrees of freedom to start with. Yet, we can still divide it into a shape of a triangle, possibly, and an orientation. Because if you think about it, if I think about it, I haven't thought about it before, but if I think about it now, as you ask me, let's take a fresh page here. So here are the 2 heavy points. And the light point, suppose it's here. But it could be anywhere on this circle, which goes around this axis. All of these points would give us the same triangle. So we can also try to make a decomposition here of a shape and or geometry and orientation. Only here there would be some differences. It would be simplified. We surely would have fewer degrees of freedom because we want to have altogether at most 3 degrees of freedom. So clearly, if we know already the positions of 2 bodies, then we'll be interested only in a 2-dimensional subspace of geometry space, and also we'll be interested in fewer angles for the orientation. So I'd say that could be very interesting to think about it more, but that's what I can say out of the top of my head. Thank you for the question. Any more questions?
Yes. So another question. Yeah.
Yes.
Sorry, I'm driving. This is why I'm not video. Sorry.
Careful.
So another question is so effectively you also define now. You can now define a metric, right? In this space, and define the distance between different types of orbits, right?
We have a metric in geometry space. It's between different kind of triangles, not between different kind of orbits, but different points in geometry space, each representing a triangle geometry. And you have the kinetic term, you can think about it as a metric. You're absolutely right. Was that the question, or I stopped doing it?
No, it was just to clarifying to myself first, and the question, it's not really a question, but I was wondering whether what use can we actually make of this metric in order to learn about the motion, for example, if you use it for the three-body problem.
Yes, so let me show the relevant formula. The relevant formula is L0. So when we look at this expression, when we look at this expression, the kinetic term in geometry space depends on theta, phi, and r, where I depends on r, theta, phi. Then you can, by just multiplying everything by dt squared, you can think of it as a metric. It has exactly in a standard way. Any mechanical system, the kinetic term can be thought of as a metric. And this is a metric which is conformal to the round sphere metric for this angular variables, and there is some radial dependence. Okay, great. So now we have a new formulation, and it remains to be seen if there are any reactions to it, and more interestingly, what kind of applications it would have to different branches here of, well, it's physics, it could be astrophysics, it could be nuclear physics, it could be mathematics. We'll have to see. So thank you very much, everyone.